Hello everyone and welcome back. Today we'll conclude our study of Taylor series, and that will include looking at what it means to converge at endpoints. So just as a way of remembering, we learned by the ratio test how to determine convergence on an open interval around the center. We also saw that there are times when a series, like e to the x or sine x, will converge for all real values. And there are some ridiculous series which only converge at the center. Most series will converge in an interval around the center. The ratio test promises convergence on an open interval. What we're about on this lecture is to see how we determine convergence at the endpoints of that interval. So one of the most powerful tools that we'll have to determine convergence of an infinite series, not Taylor series, but just an infinite series, is the integral test. And like so much of the work we have done before, a picture is very, very helpful here. So let me see if I can bring them in. So we're going to consider an infinite series, a sub n, where the a sub n terms are all greater than or equal to 0, and they are decreasing. So right here is my value of a1, here is a2, here is a3, here is a4, here is a5. Now, what we're doing here is approximating, or actually kind of including, all of these values in a function f of x. So f of x is essentially going to include a1 and a2 and a3 and a4. So for example, if my series is 1 over n, then my function is going to be 1 over x. So please remember that a sequence is a set of, well, it's a function whose domain are the positive integers. So it's just discrete values. A function is continuous, defined on all real numbers. And so this function basically is a continuous function which includes the values of that sequence. So what you notice here is that we are approximating the area under that function from 1 to infinity with LRAM. Notice also that the base of each of these rectangles is 1, and that the height is determined by the value of the series or the sequence at that point. And notice also that we have an overestimate. So what that tells us is that the actual area under this curve is going to be less than or equal to a sub 1 plus a sub 2 plus a sub 3 and so on. So that's our first important result. Keep that in mind as we move along. So I'm just rewriting what we established on the previous slide. What we're looking at now in this picture is, let's get my red pen up, this is our RAM. And you notice that this is an under approximation. And here is that's a 2, here's a 3, and 4, and so on. So what this is telling us is that the integral from 1 to infinity of f of x dx is, let's get it right, is greater than or equal to a 2 plus a 3 plus a 4 and so on. This height is a2, this height right here is a3, this height right here is a4. Okay, so another way of writing this is that the integral from 1 to infinity of f of x dx, and if I add a 1 to that, is greater than or equal to a 1 plus a 2 plus a 3 and so on. See that? So now let's put these two results together. This infinite series is greater than or equal to the definite integral there, and the same infinite series is less than or equal to a1 plus that improper integral. So let's put those two things together in a new statement. So putting them two statements together, here is what we get. And we basically have this infinite series trapped between the improper integral and a sub 1 plus the improper integral. And that is the power of those two pictures. And so therefore we can make the following two statements. So here's what we get. It's pretty simple to see. If f of x dx converges, then since this is less than or equal to a sub 1 plus that, it must converge. And if f of x, if the improper integral diverges, then since this is greater than or equal to the improper integral, it must diverge also. It's pretty easy to see. And furthermore, we see that in this case right here, this converges to some number in the interval from 1 to infinity of f of x dx to a sub 1 plus that same improper integral. So not only do we know that it converges, but we know that it converges somewhere in the interval from here to here. That's an interval of length a sub 1. So that's the integral test, and it is very, very helpful and powerful, and it's a great way to test whether an infinite series converges or diverges. Okay, so for our first example of using the integral test, let's examine whether this infinite series converges or diverges. So the integral test informs us that the possible convergence or divergence of that infinite series is exactly the same as the convergence or divergence of this improper integral. So let's look at that. This is equal to the limit, as n approaches infinity, of the integral from 1 to n of x to the minus 3/2 dx. And so this is equal to the limit as n approaches infinity of minus 2 times x to the minus 1/2 from 1 to n. Right? Because when we take the derivative of this, we get that. So we'll just flip things around a little bit. We'll deal with this minus sign, and then we'll switch these two things. And so this is equal to the limit as n approaches infinity of 2 times x to the minus 1/2 from n to 1, which is the limit as n approaches infinity of 2 minus 2 over the square root of n. And as n approaches infinity, that'll go to 0, so this is equal to 2. So therefore, since the improper integral converges, the infinite series converges. And furthermore, we know that this infinite series will converge to a number between 2 and a sub 1, which is 1, so it'll converge to some number between, let me write it down, between 2 and 3. There we go. So now we have the tools to examine the convergence or divergence of the harmonic series. It's only one harmonic series, and it looks like this. 1 plus a half plus a third plus a fourth, and so on. And a lot of folks will think it does converge because these numbers are going to 0. And you may remember that I have stated in the past that just because the terms go to 0 does not necessarily mean that the series converges. So what we do is to examine this harmonic series, which we can write as that. We simply look at the related improper integral. And we'll skip a bunch of steps. So this comes out to equal ln of x, and even though it's not really proper, we'll just write 1 to infinity. And clearly this diverges. And so since the improper integral diverges, we know therefore that the harmonic series diverges. And that's a big deal. That's how we show it. Okay, so our next big deal is to talk about an alternating series and the conditions under which it will converge or diverge. So here's what we look at. We have a series as we go from 1 to infinity of -1 to the n plus 1, could be just to the n. And this is what makes it alternate, u to the n, where these u to the n's are all positive. So this will be an alternating series. And this series will converge under the following conditions. The first one is that, well, I guess we will need to say it again, that these are positive terms. The second condition is that u sub n is decreasing, and not only decreasing, but that the limit as n approaches infinity of u sub n is equal to 0. And so what we have is that if we have any series, alternating series, which satisfies these conditions, it will converge. So it's a really simple test for an alternating series to determine whether it converges or not. Much simpler than other types of series. Okay, so now let's talk about the alternating harmonic series, which is the same as the harmonic series, except the terms alternate in sign. And we asked the question, does this series converge or diverge? And it should be really simple. By Leibniz theorem, okay, so if you think about this, each of these terms is positive, each of these terms is decreasing, and these terms are indeed going to 0. So therefore, by Leibniz theorem, the alternating harmonic series converges. Very, very simple. And so now we know that the harmonic series diverges and the alternating harmonic series converges. So now what we'll look at is what's called the alternating series estimation theorem, which gives us some idea about how a truncated alternating series provides an estimation for the actual limit. And so it works like this. If we have this alternating series where the u sub n's are all greater than or equal to 0, and if this satisfies the conditions of Leibniz theorem, thereby meaning that it does converge, and let's suppose it converges to L, then here's what this series estimation theorem says, that if we look at just a partial sum, the nth partial sum, how much does it differ from L? Well, it differs from L by less than or equal to the next term. And there's a very simple, easy visual way to look at this, because each term either pops above or below the actual value of the limit. So if here is the limit, and here is the nth partial sum, then the n plus first partial sum is here. And the difference between these two is simply u sub n plus 1. So it's a very simple graphical argument for why this statement is true. So for example, if we use the first 100 terms of the alternating harmonic series to approximate whatever its limit is, we know that it's within 1 over 101 of the actual limit. And so finally, now we're at the end of chapter 10, and we have all the tools that are necessary to answer the question, which is, what is the interval of convergence for a Taylor series? Notice the distinction here. We no longer are talking about the radius of convergence, but this is the interval of convergence, and this has everything to do with endpoints. Okay, so let's look at an example or two, and hopefully it will begin to make sense. Yeah, I think I spoke too fast. So before we look at an example, let's just talk about the general rule for doing this. Okay, so here's our goal. Let's find the interval of convergence for this Taylor series centered at C. So part 1 is that we're going to use the ratio test to find the values of x for which the series converges absolutely. And as we have said before, usually this will be an open interval about C. It might be all real numbers, and it might be just C, but it'll always be, well, not always, but when it's an interval, it will always be an open interval. And so this is where we need to test the endpoints. And so the second part is to test for convergence at each endpoint. And that is where the ratio test fails to give a conclusion, because at the endpoints is where the ratio test will give a limit of 1, and we've already talked about the fact that the ratio test giving a limit of 1 is inconclusive. Okay, so I think now we're ready for an example. So what we want to go through here is finding the interval of convergence for the function ln of 1 plus x, whose power series, Maclaurin series, looks like this. Okay, so we'll do some work and we'll get you caught up. So here's what the ratio test tells us. What we have is the limit as n approaches infinity of the n plus first term over the nth term. And what we want is for this to be less than 1, and we're asking for the values of x which make it be so. So we can simplify this a fair amount, and we've already done this before, so we get down to the fact that absolute value of x is less than 1, which means x is between -1 and 1. And so here's what we know. Let's try to keep it straight. In this interval, this series converges absolutely. What we want to check now is, does this Taylor series, Maclaurin series, converge at -1 and converge at 1? So this is where we have to check the endpoints. We do it like this. How about if x is equal to -1? We go back up here and we put -1 in for x. And if we do that, our series now becomes -1, minus a half, minus a third, minus a fourth, and so on. So this is essentially the opposite, the negative, of the harmonic series, and we know that this diverges. So therefore at -1 we have strict inequality. How about if x is equal to 1? Then we have the series 1 minus a half plus a third, right, minus a fourth, And that is the alternating harmonic series, and that converges. So therefore, what we know is that this also converges at 1. Converges conditionally at 1. And so therefore, our interval of convergence is greater than -1 and less than or equal to 1. And just for giggles, this is called sometimes a Clopin interval. Closed at one side, open at the other. And so that's the basic idea, what we're doing here. We're checking the endpoints, we're looking at the specific series that we get when we plug the values into the original series, and hopefully we get something as easy as this to determine whether we have convergence or divergence. Okay? Okay, so let's look at another example. So here we have another Taylor series, and we're asking to try to figure out what is the interval of convergence. So we begin as we always have by saying what's the limit as n approaches infinity of 3x minus 2 to the n plus 1 over n plus 1 all over 3x minus 2 to the n over n. This has to be less than 1, and we're asking what are the values of x which make it be less than 1. So I'll skip a bunch of steps and show you where we get to. So this ultimately comes down to absolute value of 3x minus 2 has to be less than 1, and that means that x has to be between 1/3 and 1. So at any time you might want to just press the pause button and make sure that you follow how I'm getting to where I'm getting. So as we've said, here we have absolute convergence. We need to check the endpoints. So here we go. Check the endpoints. How about if x is equal to 1/3? I go back up to here, and I let x be 1/3. That makes this chunk minus 1, and do you see what we get? We get minus 1 to the n over n, which is the alternating harmonic series, and this converges. So therefore, we get convergence when x is equal to 1/3. How about if x is equal to 1? So if x is equal to 1, we go back up here. If x is 1, 3 times 1 minus 2 is just 1. And I hope you see that we get the harmonic series, which diverges. They're not always all this easy, but these two seem to be that way. And so here we have strict inequality, and here is our exact interval of convergence. So believe it or not, that concludes Chapter 10, and there are just 3 quick little sections to go left in the entire BC Calculus course. We're almost there. See you next time.